Yes, hello. My name is Ercp-Net. I'll go very fast through my paper review because of time. Ercp-Net. This is my title, and Ercp-Net, and this Ercp-Net is a model that was used in this paper, and this model has a channel extension. It works with a channel extension residue structure plus an adaptive channel attention mechanism for plant leaf disease classification. I'm going to explain all that in the coming slides. The keywords are CER block, Ercp-Net, SCA block, BIF block, Scrum, CBAM. All those are models that were used in this paper, and I'm going to explain each model. Yes, before the computational problem, I'll first explain this model. This model, it is just a specific neural network architecture that is designed for plant leaf disease classification, and this model also incorporates a channel extension residue structure and an adaptive channel attention mechanism, which helps to improve its ability to classify the plant leaf diseases accurately. First, I'll go through the computational problems, and we have channel expansion and residue. Our structure is about expanding the channel, and expanding the channel is like you are expanding the channel is like you are increasing the number of channels, and those channels are where these are channels where input data is placed or received within the model, and we want to increase this number of models, the number of channels, without increasing the number of parameters, because when you increase the number of parameters, also it will require the model to learn more, to also first learn the parameters. But so this channel expansion and residue, we have a block that solves this computational problem, and it is the CER block. It is coming. I'm going to talk about it. So researchers wanted to address this challenge of increasing the number of channels in deep learning models without increasing the number of parameters, because increasing the number of parameters increases the computational burden and gradient information disappearance. Then we have feature extraction. Feature extraction, this one is like, remember, we are having image data. So images information needs to be extracted from the images, and this information includes color, we have the texture and shape, and we use that to classify the images accurately. So we need to also solve that problem. And then we have the attention mechanisms. Attention mechanism is our model also works with attention, and this attention is that the model will focus on the most important information and leave the useless information, or it focuses mostly on the important information. And also another computational problem, we have multi-perspective information fusion. And so here in this, the model focuses on both semantic and pixel level information, pixel level details. That is, the semantic is like which features in the image are considered when making a prediction, and those features may include will include the color, and then yes, the color, the shape of the leaf or the image, yes. And then we have the model interpretability. So model interpretability is like learning how the model comes up with its decision. And in this model, they use the GradCam. I'll explain it in the coming slide there. So this GradCam is like how the model makes, what features does the model consider to come up with its predictions or decision, the final decision. Yes, those are the 5 computational problems I saw in this paper. And then I'll go straight to the models. The models, we have the CER block, and this is the channel extension and recalibration block. And this model, you can see in the diagram, its purpose is just to extract images, to extract information accurately while reducing the number of parameters in the network. So this CR block solves the other computational problem of increasing the number of channels without increasing the number of parameters. That is, and that helps to the model to make accurate predictions. So this CR block has the information image future information extraction layer, and that layer has 3 max pooling layers, and then it also has the information aggregation layer that has convolutional layers of sizes 1, 3, and 1. So the image is put in this orange rectangle, as this is the input, and then we shall get the final decision from this side on the purple rectangle. That is the CER block. And then we shall go to the Ercp-Net. The Ercp-Net is the backbone of the network, and it is based on the CER block. It is constructed based on the CER block. So that its purpose is just, it is the backbone, and so it includes 2 downsampling layers and 3 CER blocks, as you can see. And then it receives images of the size 416 times by 416, which images, those are the pixels, and they are processed through a convolutional layer having a stride of 2, and then the max pooling layer having a stride of 2. And then, so this extraction helps to remove the meaningless information and also improve the discriminative channel information, and that is through the CER block, because it focuses on, it extracts the future information from the images. So this we have the SCA block. The SCA block, it is the adaptive channel attention. As we said, attention, our model works with attention. So this model is just designed to enhance the focus of the backbone network on leaf disease information and reduce interference from the redundant information. So the attention is placed, it is placed on what? The attention of the model is placed on just it is placed on the leaf disease information, and so the redundant information, and that is information that it will not be considered when making a prediction or a final decision, is not considered here. So we shall go to the component, we shall go to the the residue connection. It has also the residue connection. The residue connection in this SCA is just introduced to combine the gradient information of the CRC block with the output information of the attention module, while preserving the original state of the gradient, as you can see in the image above. And then we have the Ercp-Net. Ercp-Net, this is also a model, and this model is based on the CER block and the SCA block. So these models are all just combined together to form one big model that we shall see in the coming slide. So the Ercp-Net is constructed based on the block, and it serves as the network for classifying the plant leaf diseases, and its structure is explained. It comprises 3 SCA here above the SCA block. The SCA block is placed behind after the CR. This structure the out redundant information and on leaf disease features, and enhances information between the feature maps, and also improving the classification accuracy. So we have Ercp-Net, and this final model CP is extended residue channel pathway. Yeah, so this illustration shows all the other blocks that we have been talking about. We have the CER block, we have the SEA block, but this ERCP block only introduces the BIF block, and the BIF block is the core of this net, of the ERCP net, and it is responsible for fusing semantic and pixel level information. Remember, we are following our computational problems, so this BIF, it is the one that that makes this model to focus on semantic and and what semantic and pixel level information. So it combines feature maps from different stages of the network, focusing on both general context and specific details of the image. Yeah, and then this model also has max pooling layer. It has global average pooling, and this operation is the spatial dimensions of the feature maps to a single. It reduces the spatial dimensions of the feature maps to a single value per channel. That is, it helps in summarizing the information in the feature maps and reducing the computational complexity. And then it also has the fully connected layer, and this layer takes the output of the global average pooling operation and performs classification based on the extracted features. So it maps the features to the output classes. And then we have the softmax activation, which is this one next to the result. So it is just applied to the output, to the output of the fully connected layer to convert the raw scores into probabilities, and this helps in interpreting the output as probabilities of each class. The evaluation metrics used in this included accuracy. This one measures the proportion of correctly classified instances. So, and the high accuracy would indicate that the model is effectively classifying the plant diseases. And then we also had the precision and recall. The precision measures the proportion of correctly classified positive instances. Those are the diseased plants amongst all the classified instances. And high precision here would indicate that the model predicts a plant is diseased, and that when the model, it indicates that when the model predicts that a plant is diseased, it is correct most of the times. And then for recall indicates that when the model is that the model is effectively capturing most of the diseased plants in the dataset. That is when there is high recall. So the strength of the Ercp-Net model, it had high accuracy because it was compared with all the state-of-the-art methods. Those are the state-of-the-art methods are like the VGG, the ResNet. Yes, it was compared and it had higher accuracy. And then it has the multi-perspective feature fusion. That is because of the BIF block that is in the ERCP, which allows for integration of multiple perspective information, which enables the model to focus on both semantic and pixel level details. Yes, and it makes the model to produce robust predictions. Then we have visualization with GradCam. I told you GradCam. The model was using GradCam for visual analysis, which provides insights into the attention regions of the model. That is, it helps the model to understand how it makes predictions based on input images. And then another strength is that it has comprehensive evaluation. It is using 3 evaluation metrics to evaluate the model's performance. And then the weaknesses of the model, it had a lower, we have, okay, for the weaknesses we shall take model per model. So Ercp-Net, it had a lower accuracy on the AI challenger data set, indicating potential challenges in generalization. And then this means that the model will struggle with certain types of images or data sets. And then Ercp-Net, this one struggled with fine-grained information in images, thus indicating limitations in capturing the detailed features of plant diseases. Then the model may have difficulty in distinguishing between certain categories of images or diseases. Then the Ercp-Net, for its weakness is that it had difficulty in distinguishing between certain categories, such as the cone grey leaf spot and the cone northern leaf blight. Yeah, so I'll go to the visual analysis. These were images in the paper. So visual analysis here shows that leaves with different and then the second row was indicating the Ercp-Net model output of the Ercp-Net model, that is, and then the third row was for the output for the Ercp-Net combined with CBAM, and then the fourth was Ercp-Net, that is what it output. And you can see that in all the inputs, the Ercp down on the fifth row had the best output of the diseases, of the disease classification. So this is an explanation of the heat map. So this one is a comparison between the model, our model, the Ercp-Net model, with other models, and it shows that we had better accuracy in the AI challenger dataset, and then also in the plant village dataset models, our model had the best or highest accuracy. And then this Ercp-Net model works with an app, and this app has a user interface that provides a user-friendly interface with an information display box and a picture upload button. So here you upload the farmer or the person who wants to know the disease takes an image of the leaf, and then he uploads it, and then this app is integrated with our model inside. So when you just take a picture, and then the model will give you results based on the model's prediction within the app. And this here is the result of the prediction. These are the result of the prediction. It brings you back with category of the plant, that is the name of the disease, and then the confidence it has in its prediction, then plus the time it took to make the prediction. So the server runtime and app runtime, this graph here is just showing that because this model can be used on the computer, that is on the web browser, and also on the app. So the red one is showing the time it takes. We can see that when we use the app, it takes more time to give a prediction than when we use a browser to make a prediction. And then this is the reference of my paper. Yes, thank you for listening. That's all I had for you. Have a good evening.